Hey, hi everyone, this is Vivek, and today we're going to talk about this yet another minimization problem, which is a very beautiful problem on expression manipulation and how do you derive or reduce some given problem into a known problem. So let's get into the problem. And apart from this problem, there is always going to be this standard setup of these series, Codeforces weekly series, that whatever you learn in this video, there is actually two learnings that you should definitely learn from this one. Make sure that you comment them down below so that you kind of retain them and encode them for a very long time, right? Let's get started with the problem. Let's say there are like this two array given to us and of size n each, and we have this operation which is given to us at in which we can select any index and we can swap ai and bi, right? And we need to like minimize the sum of these two things. For array a, the cost is defined as sum of all pairs squares, and for b as well, it's a similar metric. Sum of all of those two things we need to minimize altogether, and what is the best we can do is what we need to tell. And the number of numbers is up to 100, ai is 100, bi is 100, right? The constraints is all hundreds sort of thing. Now like obviously the setup makes sense, and if we kind of go through the example, like let's say this is the array, this is the array, then with 2 you kind of pair it with 6, you pair it with 4, you pair it with 6, and so on, all pair sum square and so on, and then you get the final number. That's what we need to minimize, right? So this particular problem is straightforward in terms of what it means, but again, when you try to see the constraints, it's kind of leaving out a wide variety of options with us. Like it might be greedy, DP, it might be brute force, it might be something else. Not really brute force, because like the options are 2 to the power n, so it cannot be a brute force problem, but still there are a lot of options left without that. Well, whenever I see these problems with 100 kind of constraints, right, immediately something that should click in your mind is DP, because DP is a natural choice for these kind of things, because having a constraints up to 100 leaves out room for creating so many states altogether, right? You can keep so many things as a tracker in the state so that you can generate solutions, and that's something we're gonna explore more. But first of all, there is this weird kind of an expression that we are seeing for the first time almost, which is summation of all pairs square, which is not something which is a very standard metric in general, or very standard metric or standard expression that is used as a cost function for a lot of problems. So let's try to understand how this kind of dissolves into. So this was what we do in the reading phase. If you have not seen the previous video, do check them out. But we use this flow that we have this reading, then we have this formulation, we have this observation and solving phase, then we have this formulation phase on how the code is gonna look on a global level, right? And then we're gonna code this up and debug. But the coding and debugging is something that I leave out for you guys. But we're gonna talk about how do we actually solve these problems, think about how do you solve them in a real context, right? So this is what we're gonna talk about. So let's move into like understanding the expression that is given to us. So the expression that is given to us is double summation. We kind of select an I and a j which is not going to be same, and j is always bigger than I up till n, and this is going to be a of I plus a of j whole square. So this is the double summation that we are given for a particular array, and it's similar for the B array, but let's try to focus on this particular expression over here and try to make more sense out of it, because just by this maximizing this weird metric, minimizing this weird metric, it doesn't really make sense. We need to make sure that we can get some simpler term which can give us more information on what to do. So what we do is we try to open this particular bracket, and if you understand, it's like, let's say there are, let's for now think about that there are 3 terms, right? So what we can do is it's sort of like a1 plus a2 whole square plus a1 plus a3 whole square, right, plus a2 plus a3 whole square, right? This is the terms that is given to us. Now whenever we open this up, we're gonna get something like, let's say, ai square plus aj square plus 2ai aj. This is the standard a plus b whole square formula, and then there is a double summation on top of this, right? Now if you try to understand what happens over here is this ai square, okay, when you write this double summation 1 less than n, right, ai square plus aj square, right? Let's write this particular term, okay? So let's try to see how many times a particular I or j, like for a particular number x appears in this. Let's say how many times a of x is going to appear in this particular term over here. Okay, it's basically just the ai square plus aj square double summation part, and this particular part we will evaluate separately. But let's first understand how many times some x square is gonna come up over here, right? So it's double summation ai square plus aj square, where I is less than j strictly, and it's all pairs kind of thing. So it's going to be 1 2 3 4 dot 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 1 2 3 4 dot dot dot, it's I and this is j, let's say. So for I equal to 1, j, this is going to be present, this is going to be present, this is going to be present, right? For I equal to 2, this is going to be present, present, and so on, right? For 3, this is going to be present, right? Now if we try to focus on any particular, like a of I, okay, like number 2, the number of times it is going to appear as a of I, okay, is going to be nothing but, over here the number of times there is a possible j. So a particular a of x square is going to be present as a of I square for all possible j's bigger than that. So for any particular x, the number of numbers bigger than that is nothing but n minus x, right? Number of possible values of j if x is equal to I is nothing but n minus x, right? And the number of times a of x square is going to appear as j is every time there is a possible value of I. So the number of times it's going to appear over here is nothing but the number of possible values that is less than x strictly, which is x minus 1. So this many times it will appear as a of I, right? And this many times it will appear as a of j. If you sum this up, the number of times ax square is going to appear in this all term. You can see that over here there was 2 and over here there was like n minus 2, n minus 3. Over here, so over here this is n minus 2 and this is let's say, so over here, sorry, for 2 we are kind of calculating, right? Over here it's 1. So n minus 2 and 1. If you see for 3, it's going to be n minus 3 times, and there are 2 times over here. So a of 3 is going to be n minus 1 times. So any a of x square is going to appear n minus 1 times altogether, right? So you can simply evaluate that from this expression also. Also, you can see this matrix on how many times a of I and a of j is going to take a particular value and then get it up. But the simple term that we finally get is any ax square is going to appear n minus 1 times in this double summation over here, right? So this is something that we can write directly going back, that the expression that we wrote over here is nothing but n minus 1 times double summation of ax square for x in the range n to 1. Right? And which is something that is kind of independent of like pairing, right? I mean, it's every value independently. We'll see this. We'll see how this kind of boils down finally. Let's try to see this second term over here. So as of now, we have written double summation a of I, a of j, twice of this, plus the other term was double summation of a of I square plus a of j square, which finally boiled down into a of x square, right? For x in the range n to 1, right? This is something that we get over here. And this term appear like every a of x appears exactly n minus 1 times. There is this particular term that is left, wherein in this particular part also I is less than j. How do you kind of use this particular metric over here? This is the most beautiful part of this particular problem. Okay, so see over here we have 2 a of I, a of j, right? And I is less than j. Let's see, we write it this way: 1 2 3 4, right? 1 2 3 4. So the way it is going to be present is, so this is the value of a of, the cell contains a of I into a of j, the number of times it's present, right? So as of now in this whole term, this is going to be present twice, like the coefficient is 2, 2, 2, 2, and all of these things are 0, right? So a of 1 into a of 2 is present twice in this double summation. A of 1 into 3 is, a of 1 into a of 3 is present twice, and so on. This is the double summation, and this is what is kind of given to you in over here. This is the summation that we want over here, right? Now we all agree that a of I into a of j is same as a of j into a of I, right? Now a simple manipulation that we can do is we can kind of convert this particular 2 into a 1 and this particular 0 into a 1. Okay, why? Because this is 1 into 2, this is 2 into 1, and these two are kind of giving us the same value altogether. So we can say that this is same as this. And in fact, this is something we can do, that we can shift this one from over here to over here and the value remains the same. So we can also see this double summation from a lens of seeing this as 1 to 1 over here, right? And I'm just going to quickly change all these values. So the original double summation that we had is also same as this matrix over here. Like each of these coefficient tells you how many times that particular product is going to be considered, right? This is the matrix that we are kind of adding over here in the double summation. And this is nothing but the seeing this from the lens of instead of removing this two, keeping this two, removing it off, and then adding like few terms over here so that it looks something sort of a symmetric matrix, right? Now there are these weird zeros in between, and if you think about these zero positions, it's nothing but a of 1 into a of 1, right? So it's zero number of times. But hey, we have a of 1 squared over here, n minus 2, n minus 1 times. So what we can do is, to fill these zeros with ones, we can kind of borrow and like 1 from over here and then put that in this double summation and fill these values with ones. So essentially what we can do is, we can kind of write fill these values with 1, right? Fill these values with 1. And we can make this particular thing as n minus 2. Why? Because every particular square was present over here n minus 1 times. We borrowed a of 1 square once and then put it in this particular matrix. We are writing this double summation in the form of a matrix. Please try to understand what this means. It's essentially the count or the coefficient of a of I. This is a of I, the I value is over here, and this is a of j value is in this side, right? And what is the coefficient of that? We kind of borrowed off one element over from this side and then put it over here, right? And now the whole like magic happens, because when you have this full matrix over here, you can see that a of I gets multiplied with a of j altogether over here, right? With all of values of a of j, a of I, a of j plus a of 1 plus a of 2 plus a of 3 plus a of 4. So if we try to like see what this kind of a matrix, all ones kind of a matrix dissolves into, like if you try to see, then a of 1 gets multiplied with a of 1, a of 2, a of 3, a of 4, and so on. So what we can write is a of 1 multiplied by a of 1 plus a of 2, so on up till a of n. Then again, a of 2 is also multiplied with a of 1 and plus a of 2 into a of 1 plus a of 2, so on up till a of n, right? Every term is kind of a of n multiplied by a of 1 plus a of 2, so on up till a of n. And this is nothing but a of 1 plus a of 2, so on up till a of n. In the first term, we kind of take all of this particular part common from all, and it's the same thing on this side also. So it's sort of this, which kind of reduces into summation of a of I whole square, right? So the magic happened when we kind of took one a of x square summations from this side and moved it to this particular part of the expression, and suddenly this expression became a of x summation of a of x whole square, which is the main beauty of this problem. So the actual expression that was given to us, which is double summation of a of I plus a of j whole square, I less than j, is equivalent to saying it this way, that we have n minus 2 times the summation of ai squares, right, over here, plus 1 time that we had this double summation plus 1 taken over from this side. So that particular part altogether gives us this term over here. So we can write summation of a of I whole square. So this is the final value that we get from this expression, right? So this is something which you had to do in this particular problem before you could make the actual make the final usage of technique into this problem, because unless you see this form of an expression, there is no observation altogether that you can directly draw, because all pair kind of cost is something that is difficult to digest and even manipulate directly. So this is something which is much more manageable, that each of a of I is independently interacting instead of being with pairs. So this is something we get. And then we also have, so note that this is the first one, and then similarly we also have n minus 2 times double summation of b of I whole square plus summation of b of I whole square, right? This is also there, because the second array also needs to have a cost, and the sum of all of these is what we need to minimize. And note that for a particular a of I comma b of I, the option that was given is we can swap these two values in its own place. Now understand what this swap can change, right? If you swap something, a particular b of I square will kind of move to this a of I square, and a of I square will move to this b of I square. So in total, in the whole sum, nothing is gonna change. Like there is this particular part which is summation of a of I square plus b of I square, right? There is this particular part if you kind of club these two terms together, right? Note that even if you do the swap, nothing changes in each of these values. So there is altogether no change if you do a swap to this part of the expression. So this is something which is fixed for the problem, and there is no like effect of the operation on this. The only thing that will change the way you are going to decide the values is the distribution of the summations, and the squares is going to depend on that. So the thing that we are focused more on is this part, which is summation of a of I square plus b of I square, which we have to minimize because this part is fixed. This is fixed. This is a of summation of ai whole square plus summation of bi whole square is what we have to minimize. So the final problem boils down into, we have summation of ai whole square, right, plus summation of bi whole square. You have but like kind of an a array wherein you have some array elements over here, you have b array which has some array elements over here. For any particular position I, you can swap these two values, right? After swapping any number of operations, you have to finally minimize this particular value, right? And that's the main problem now. So this is now an algorithmic task, which is a very standard problem once we see how it looks, but this is the main like kind of decomposition. So before moving to this particular part, you have to first do this like expression manipulation, and then finally get to this part where you can see that this is constant, this is variable, and this is what you have to optimize. And then finally, once we have this place, we simply recognize that this is a very standard problem. How? You are given that a of I is up to 100 and n is up to 100. So this immediately calls that when you can kind of find out, based on all possible swapping, what are the different values of sum you can attain, right? This is a very similar problem to knapsack kind of thing, or subset sum, right? There is a subset kind of a sum problem being formulated over here. How? That let's say you are kind of at the first dp of, like you are at a state, I'm just gonna give you an idea. This dp is pretty straightforward. You're at the state that you have taken 0 item and you have 0 weight altogether. So for the first item, you can keep let's try to see what are the different weights we can create for this array. Weights as in the sum of the values that we can create for this array. So either you keep ai in it itself, so you go to position 1 and you keep a of I, or you take swap and you take b of I into it, so 1 comma b of I, right? Then again you have option that you can take a of 2 or b of 2. So in this case, you're gonna go to position 2 and you're gonna move to a of 1 plus a of 2, or you're gonna go to position 2 and a of 1 plus b of 2. So all possible things that can be generated will be generated this way. And this is something which is sort of a subset sum problem in dp. You can kind of google this up if you don't know about subset sum, but it's essentially like finding out the different possible subsets that you can create. And there are a lot of neat ways to do that. Like you essentially write a dp that you can write it this way, that if I try to write a recurrence for dp, recurrence of I, just wait, there is another interesting observation coming forward. I comma sum, right? So if you have all the items that is from I till n, can we make this sum, yes or no? If I take a of I, then I need to make recurrence of I plus 1 from the next item to the end. Can I make sum minus a of I? And if I take the b of I by swapping it, then can I make I from I plus 1 sum minus b of I? And note that the sum can only take up till 10 to the power 4 values, because there are 100 items and each item has 100 value. So the maximum value of sum is this. I is 100 and the choices are only 2. So the total complexity would be 10 to the power 6, 2 into 10 to the power 6 kind of in complexity, which is fine for a DP, right? And one more thing that we need to understand, I mean, this is actually sufficient to solve this problem, but there is one more quick trick that you can learn for this kind of a problem, that when like in this setup, the sum of a of I plus sum of b of I is fixed, right? I mean, this is equal to like the initial sum. So it's fixed. It's essentially saying like x plus y is fixed, and you have to minimize the value of x square plus y square, right? You have to minimize this. And this happens when both of them kind of, this square sum minimization happens when both of them attain almost the similar value. So you have to make actually a of I, summation of a of I closest to the half of the sum. So you have to make it as equal as possible. That's another greedy observation that you can use for this problem, but it's actually not required because we can iterate on all possibilities. So there is no requirement for this, but also keep this in mind in case it is used in some problem that when x plus y is fixed and you have to minimize x square plus y square, you have to actually make x and y as equal as possible, because in that sense it's more equal. I will leave this as a to proving this as an exercise because it's not really required for this particular problem, but you can kind of try to see why this works, right? So that is there, and this is a standard DP. So let's move on to the final formulation. So let's create a formulation one. So if you want to formulate this up, a very simple thing that we see for this one is, let's say we have the setup that we take the a of i's and b of i's, and then what we do is we simply evaluate n minus 2 times summation of a of I square plus b of I square, like for every position, you know this metric. This is fixed anyways, swapping doesn't really change, plus you have to minimize a of summation of a of I squares plus summation of b of I whole square, right? This is what we need to minimize because this is fixed. And now once this is the main problem, simply instantiate into a new function maybe where you pass in the values of a array and b array, and it has to minimize this metric. To solve that, you have to use a DP, which is subset some sort of a DP, wherein you have to find every element either takes a of I or b of I, and you have to make the subset sum. You have to find all possible subset sums that you can create, and then using that you have to just plug in the value and see what gives you the minimum. You just try to find out all possible values of this. There are 10 to the power 4 different values. Put all of them over here that are feasible, and then you will get, this is nothing but summation of a of I plus summation of b of I initial minus the, let's say if you put the value x over here, this is going to be this. So it's fixed. If you put x over here, and using that you can get the final value. And this DP works in order n into ai, n square into a, right? N into ai is the maximum value, and again n for the level 1. You can actually make this divide by 32 or 64 based using bit set or a custom bit set if you want to, and then make it a bit more easier, because this DP returns nothing but can you make it yes or no. So it's a boolean value, so you can use a bit set for every layer, but that's an optimization that we can cover up in some other video maybe. But for now, this is all that is there for this problem. And then finally, when you get this minimum, just plug it in this expression and you get the minimum value. So that's, I guess, all for this particular problem. The expression evaluation was pretty interesting. I think there are a lot of learnings in this particular problem. So now it's your time to learn and kind of comment down below what you learned altogether in this. Don't forget to like and subscribe to this channel, because whatever we are creating, it is kind of going to be continued for the next few weeks. And if somebody is learning at least 3 new techniques every week, I feel that within a good, a short period of time, you're going to learn so much of techniques that you're going to see the improvements soon. Right? So stick with this particular channel and keep solving the problems that are there on the weekly, on the 3 weeklies at Coder, Codeforces, and LeetCode. Also, a small announcement: if you guys are following, for those who's watch the videos till the end, so we have hit this particular 5K mark, which is remarkable. I mean, I personally did not think that just creating educational content is ever gonna make me reach 5K, which is pretty awesome. I mean, I do teach in general to help even some people who are watching my channel, because I understand that at this intermediate stage there is a lot of not a lot of viewers. If I start creating a lot of beginner contents, maybe a lot of people would flock onto the channel and would be interested in the content, and maybe in future I can create. I'm not saying I will never, but I personally feel that there is a lot of less channels which are creating content at this level, at the intermediate or the zone where you already know a lot of techniques, you know the standard techniques, but you need to know that extra you need to load up your arsenals with some techniques that are actually competitive, right? So that's what we try to cover in this channel. In fact, I have kept in plan that we at right now have 3 videos per week, right? So if you guys want, maybe we can increase that to 4 soon enough, but I was thinking it's gonna be something that we start once we hit some other mark as well. So I'm gonna declare that up very soon. I have something more planned up for this channel. So thanks for supporting up this channel for this long, and hope we grow together. And feel free to let me know what are your views on the channel, if you have some suggestions for me, if you need any thing which is there. In fact, I know that a lot of people write in the comments that these Vivek make videos on series, on topics and all. I do think that some topics do have good videos, some topics don't have, and I'm I try to target those in most scenarios. These are like recent contest questions, so that you kind of learn the recent techniques that are being used to formulate questions. And I find a lot of new techniques. I'll go through the problems. In fact, in this contest, you can go ahead and try to see the E question. It's also like a little harder than this. I thought I could cover that one as well, but again, it might be a bit more difficult, so lesser people might find it interesting, and there are so many observations in that as well. So go ahead and solve these problems. D is like a good set of problems that you can kind of solve and learn a lot of techniques, right? And I understand that for some people it might be difficult at the start, but it's essentially this like out of comfort zone practice that essentially makes you a better programmer, right? So that's all for today. Thanks for joining up, and see you in the next video. That's all for this fourth Codeforces Weekly. We have made it 4 weeks. We'll keep continuing learning, right? So that's all. Bye bye. See you in the next one.